Hello everyone, I am Dr. Saikat. Today we will discuss about one topic of chemical bonding, that is Fajan's rule. Fajan's rule was dictated by K. Fajan's rule. So what the rules tells? Fajan's rule actually dictates about the introduction of covalency in ionic compounds. So covalency introduction, how we can generate covalency in ionic compound, because in ionic compounds formed by cation and anion, and it is a cation of one atom and anion of one atom are joined or attracted by electrostatic interaction of Coulombic interaction. But in covalent compound, the covalent bond is formed by sharing of two electrons between two atoms. The one atom gives one electrons, and for single bond formation, one atom gives one electron and another atom donate one electron, and they are mutually shared, the electron pairs are shared and the covalent bond are formed. But in the ionic compound or ionic bond formation, the cation donates the electron and anion accepts the electron, or one atom donates the electron and forms the cation, and another atom accepts this electron and this forms the anion. So covalency in ionic compounds generated by the Fajan's rule. So from the pictorial description, suppose I am taking one cation. So cation, this size of cation is small with respect to that of the size of cation is small with respect to that of the anion, because the number of photons inside the cation or in the nucleus, the number of photons is greater with respect to that of the electron. So as a whole, the nuclear charge or the positive charge density is greater with respect to that of the surrounding electrons. So the positive charge attracts the electron too much, and as a whole, the size or the radius of the cation decreases. But for the anion, the number of electrons is much more compared to that of the number of photons available in the anion. So as a result, the positive charge density is less with respect to the negative charge of the electron. So as a whole, the charge size of the anion increases. So that's why the cation showed here is very small, but anion size is larger. So what happens as the cationic charge density is cation's positive charge density is greater with respect to that of the anion. So when the cation and anion comes closer, so the positive charge of the cation attracts the electron density of the anion. So the electrons in the structure of atom we called as a electron density. And the quantum mechanics we call as the electron density. So it attracts the electron density, the positive charge in the cation attracts the electron density of the anion. So it pulled the electron density towards the cation. The electron density of the anion is pulled towards the cation. So this is the phenomena is called as a polarization. So this is called as polarization. The phenomena is called as polarization. So polarization happens by the cation. So polarization or electron deformation of the anion is happened by that of the cation's positive charge. So as a result, due to this polarization, the electron density of the anion is pulled towards that cation, and as in several steps, it is completely goes into the electronic region of the cation. The negative charge or the electron density of the anion goes into the electron density of the cation. As a result, as the electron density comes into the cation, and as for the electrons of the anion is shared by that of the cation and anion itself. So when the electron sharing happens, that's why the covalency is generated, because in the covalent bond we know that the electron sharing happens. So as a result, in several steps, and then in the last step, the polarization or the covalency is happened. So due to this polarization of cation, so the polarization of cation is called as polarizing power, because it polarizes or deforms the anion of the electron, deforms the electron of the anion. So polarizing power, it is called the polarizing power, and for the anion case it called is the polarizability. So the polarizability happens for anion, but polarizing power of that cation. So this is the polarizability. So polarizability means the deformation of the polarization of electron of anion happens. So that is called the polarizability, is term defined as the polarization happens for anion. So polarizability for the anion, and the polarizing power means who is polarizing. That means the cation is polarizing the electron density of the anion. So that's why it is called the polarizing power of cation. So for different types of cation and anion or the molecules, so how the covalency varies. So there is a terms we are defining. So the term here we are defining is the ionic potential. Ionic potential. So ionic potential means ionic potential equal to charge of the charge of cation's charge, or charge of cation divided by radius or size of cation. So ionic potential is only for the cation, not for anion. So ionic potential is given by the symbol phi. So ionic potential is defined by the charge of cation divided by radius of cation or size of cation. So from the pictorial diagram we see that if the small size of cation and the large size of anion happens, whatever, or the size, if the size of the cation is very small, or with the decrease of the size of the cation, the polarizing power increases, because that's why the positive charge density of the cation increases, so it attract more the electron of the anion. So decreasing the size of the cation or increasing the charge of the cation, the polarizing power of the cation increases. And for the anion, what happens? So with increasing charge and increasing size, so it will often more polarizable, or more polarizability will happen, because if the size of the anion will greater, then the cation's positive charge will attract electron density more, because the anion nucleus is not too much held or too much attractive power of that of the anion electron. So that's why the cation's positive charge attracted the electron density of the anion. So that's why the from the ionic potential values, so with increase of phi, that means charge of cation increases. So charge of cation increases, and as it is inversely to the inverse to the size of the cation, so with decrease is the size of the, or radius or size of the cation, the phi increases. So phi increases is defined that the covalency increases. So covalency increases. So if I take, say for example, some charge, say for example Na plus, B2 plus, L3 plus, Si4 plus. So for the given cation, so which will be more polarizing? So for the same anion, say for example, we are talking about that the anion is same. So suppose for example, for the same anion I minus, so what will be the highest polarizing power, or the polarizing power order, or the covalency order will be? So the cation charge greater, the charge of the cation increases, means phi increases, that means the covalency increases. So the covalency order will be Si4 is the maximum, then L3 plus, then B2 plus, then Na plus. It will happen. Then suppose for the group 1 element or the group 1 cation, say for example group 1 means lithium plus Na plus K plus, lithium, sodium, potassium, rubidium, cesium. So this is the group 1 cation. So from according or the down the group, the size increases. We all know that, because in the periodic table, say for example, say for period 2, lithium, then beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. This is the inert gas. So this is the period. So according to the period or across the period from left to right, the size increases, size decreases, sorry, size decreases. Size decreases, and from the group according or down the group, the size increases. There is the periodic trend of the size or radius. So from left to right, from the period, the size decreases, and from group down the group, the size increases. So that means, with the increase in the size, that means the phi decreases, because phi is inversely proportional to that of the radius or size of the cation. So the covalency phi decreases means the covalency decreases. So the covalency power will be, if the same anion I am taking, so the covalency power will be maximum for which one? So lithium plus, then sodium plus, then K plus, then Rb plus, then Cs plus. But so this is the for the cationic case, but there is no general trend or there is no general formula for that of the phi in by this of the anion, because phi is not generally related to that of the anionic charge or the anionic size. But from the physical meaning or the physically, if we analyze that the charge of the anion, with the increase of the charge of the anion and size of the anion increases, both charge of the anion increases and also the size of the anion if increases, so that will also lead to the increase in the covalency, because from the physical definition, we know that, because if the charge of the anion increases, that means the in the anion more electron density is there, so it will attract the positive charge of the cation will attract the electron more, so that will lead to the more covalency or more polarization happens. And if the size of the anion increases, so that means the anion positive charge or anion positive nucleus is not attracted or too much attracted the negative electron density of the anion. So as a result, the cation positive charge or cationic nucleus attracts the anion electron density, so that will lead to the more polarization, that means more covalency. So we can tell from that covalency increases means phi increases, and when the phi when phi will increase, so charge of cation increase, size of cation decrease, C for cation. And if charge of anion, A for anion, charge of anion increases and size of anion also increases. So this is the general condition. This is the general condition for the increase of the covalency. So suppose if I talk about some example, let us take some example. lithium fluoride, lithium chloride, lithium bromide, lithium iodide, because the charge, so which will show the more covalency or the order of the covalency, what will happen or what will be the order of the covalency. So the for the four compounds or the four salts, the cation is same, lithium plus, but the anion changes. So the according to the group, the charge or the size of the halogens increases from fluorine to chlorine to bromine or iodine, then iodine. So iodine is the maximum size, so it will show maximum covalency, because anion having the more size, that will lead to the more covalency. So the lithium iodide will be more covalent than lithium bromide, then lithium chloride, then lithium fluoride. And if I talk about, suppose for example, another example, LiF, NaF, RBF, CSF. So here the anion remains fixed, F minus. So cation size or cation changes. So lithium, sodium, rubidium, cesium. So in the group from lithium to cesium, the size increases. So with the increase in the size of the cation, the phi decreases. So that means the covalency decreases. So the maximum covalency will happen for that of the lithium fluoride. So lithium fluoride is maximum covalent, then NaF, then RBF, then CSF. So that is the general trend of the covalency concept related question. So another thing is that if the covalency increases, so covalency increases means melting point and boiling point of the salts or compounds decreases, because we know that covalency increases means no bond is purely covalent or purely ionic, because in mathematically we can tell that the 100% ionic compound or 100% covalent compound, but in reality no bond or no molecule is 100% ionic or 100% covalent, and the percentage of ionic character is in the covalent compound is calculated by that of the dipole moment. So in this connection, or now we are not discussing here the dipole moment. And the another concept is that if the covalent compound, ionic compound is generated, so in the ionic compounds how the covalency can be generated, so that will dictate by the that is described by the Fajan's rule. And another, in the percentage of ionic character is described by the what? Percentage of ionic character is described by the dipole moment. So in reality no bond is purely 100% ionic or 100% covalent. And when the ionic compound forms, ionic compound means the cation and anions are attracted or are bonded with Coulombic or electrostatic interaction, and these interactions is strongest interactions. So for the ionic bond, generally the energy of the ionic bond is around 600 to 4000 kilojoule per mole, but for the covalent compound or for the single covalent bond, it varies from 150 to 400 kilojoule per mole, depending on the substance, because covalent bond is formed by the sharing of two electrons. So as it is formed by sharing of two electrons, so its energy is less with respect to the ionic, because ionic bond is formed by the electrostatic interactions or Coulombic interactions, so it is the strongest bond. So that's why its energy is higher with respect to that of the covalent bond. So the with increase in the covalency, the melting point and boiling point means The melting means from solid to liquid, the temperature needed to convert from solid substance to liquid substance, and the boiling point is the temperature at which the liquid converts into its gaseous substance. So as the ionic compound has high energy, or to break the ionic compound a larger amount of energy is needed, so melting point and boiling point of the ionic compound is high with respect to that of the covalent compound. So with the increase in the covalency, the melting point and boiling point decreases. So that's why if I talk about some example, beryllium chloride, magnesium chloride, calcium chloride, beryllium, magnesium, calcium, strontium, barium. So this is the barium, magnesium, this is the group 2 metal. So as the anion remains fixed, the covalency is greatest in case of beryllium, because the from down the group the size of the cation increases. So barium 2 plus has a larger size, so it will go, or the covalency order will be least in case of beryllium chloride, and it will maximum for the beryllium chloride. This is for the barium chloride, and trend is calcium chloride and then strontium chloride. So as it is maximum covalent, so its melting point is minimum. So generally the observed melting point is 400 degrees centigrade. For the magnesium chloride, it will around 640 degrees centigrade. This is for the 710 degrees centigrade, this 770 degrees centigrade, and this is around 860 degrees centigrade. So with the increase in the covalency, the melting point decreases. And another thing is that if the covalency increases, the covalent bond or the covalent molecules will soluble in the covalent molecule, or the covalent compound will soluble in the nonpolar solvent. Nonpolar solvent means the polarity is generated or polarity is dictated by the dipole moment. Nonpolar means the dipole moment is 0. Say for example, nonpolar solvent, we can say that the carbon disulfide CS2, and the ionic compound generally soluble in polar solvent or polar medium. Polar means water. Water has a definite dipole moment. Polar solvent, because ionic bond means this is a polarity, a cation and anion, there is a definite dipole moment exists. So the polar molecule will prefer to soluble in the polar solvent. Polar prefers polar, and the non-polar prefers non-polar. So that's why the covalent molecule generally soluble in the non-polar solvent. So if I talk about this compound, so beryllium, or suppose for example I am taking that another example, say AgF, AgCl, AgBr, AgI. So the cation is fixed, so anion is changes. So size of the anion, as all the anion have charge same, -1. So the size of the anion increases, so that means the covalence increases. So the covalency order will be this one. AgI will be the maximum covalent. So AgI is the maximum covalent. So if I talk about the solubility in water of this salt, solubility in water, what will the order? So solubility in water will be the reverse because AgF is the mostly ionic, so it will soluble maximum in water, so solubility will be AgF will be maximum, then AgCl, then for AgBr, then for AgI. And if I tell that the solubility in carbon disulfide, so then it will go in the covalency order, because the so this is the same order is that of the CS2 solubility in CS2, solubility in CS2, but for the solubility in water or polar medium, the reverse trend is observed. So that is the different type of questions or different types of concept in the Fajan's rule. So another thing I want to tell that, so if any one can ask that for the K plus and Ag plus, suppose for this case same anion, suppose Ki or Kf and AgF. So for these two compounds, so which one will be more covalent? Covalency is maximum, or which will more covalent? So K plus is the alkali metal cation. This is the alkali metal cation or alkali metal. But AgF, Ag plus is the has d electrons. It has d electrons. Because it has something copper, silver, gold. This is the same trend in the same group, Cu plus, Ag plus, copper, silver, gold, Au plus. So these all have d electrons, because if I talk about the copper electronic configuration, so argon, (3d10), it will, so d electrons. So this silver plus, like Zn2 plus, Hg2 plus, cadmium 2 plus. So as it has the nearest noble gas configuration, like D is fulfilled, so as like that of the Zn2 plus, it also 3d10, Zn2 plus, argon 3d10. So as this is, as that compound has fulfilled D, so this compound is generally Zn2 plus, Mercury 2 plus, Cd2 plus are called pseudo noble gas configuration, because all atoms or all element will try to attain the nearest noble gas configuration. But in case this noble gas is the inert gas of the noble gas, so there is, if NS2, suppose if the electronic configuration is NS2 NP6, that means is octet fulfilled, so that is called the typically inert gas configuration. But in this case, as that no already D is involved or D is fulfilled, so this is called the noble gas type of configuration, so this is called the pseudo noble gas configuration. So as the D electron or the F electron is involved, so in this case, so when the cation has D electrons or F electrons, so what happens? Suppose this is the positive charge nucleus of the cation, this is the nucleus of the cation. So in the inert electrons, in the inert, this is D electrons or F electrons, and this is the valence shell. This is the valence shell or the outermost shell. So as the shielding power or the screening effect of the shielding effect, suppose if I tell that the screening effect order for the s, p, d and f block element or the s orbital, so s orbital as highest, then s greater than p greater than d greater than f. So as the d and f electrons has low shielding or low screening effect, so that's the screening of the shielding is low. That's why the positive charge of the nucleus or cation's nucleus will attract more the valence electron, because this screening is less, so it will attract more the valence electron. That's why the size decreases more with respect to that of the alkali metal. So with increase or the due to the presence of the d and f electrons, so that cations will polarize more or the size reduces more. That means the covalency will generated more. So that's why the for the comparison between the alkali metal and the pseudo noble gas type of cation, so the pseudo noble gas will generate more covalency with respect to that of the typically alkali metal cation. So in the given example, Ki and Agi, so Agi will lead to more covalency, so more covalent. Same thing if I talk about according to the group, so suppose Zn2 plus, Cd2 plus, cadmium 2 plus, mercury 2 plus, same anion I am taking, say for example, for in this case same anion is Cl minus. So as they are both in the all three in the same group, so from this one Zn2 plus, cadmium 2 plus, mercury 2 plus, so the d and f electrons is increases from Zn2 plus to Cd2 plus, Zn2 plus only d electrons, Cd2 plus only f electrons, and the Ag2 plus f electrons are there, so number of d and f electrons is increases from Zn to Cd to mercury. So that's why, so it will the low shielding effect will happen, so that's why it will attract more the electron of the valence shell, so the size will be reduces more, so that will polarize more. So that means Ag2 plus will polarizes more the anion, so that means the covalency order will be Ag2 plus, then Cd2 plus, then Zn2 plus. Thank you.